Precalculus video lecture number 27 on exponential growth and decay models. Now, many real-world applications follow exponential models. If you think about it, like populations grow exponentially, bacteria grows exponentially, diseases can spread exponentially, radioactive substances decay exponentially. And so the first model that we're going to look at is the law of uninhibited growth. So the model basically tells us what the final number or population is, n, after t time. N naught, this n with the subscript 0, is the original amount. And you'll see this notation in other classes as well, like maybe your physics class. V naught, that means the initial or starting velocity when t is equal to 0. A naught, that's your initial acceleration. So n naught is the original amount when t equals 0. K is our growth constant. In this case, it's positive because that means our exponential function is growing, increasing. So that's why this is the law of uninhibited growth. Now, it's uninhibited because obviously in the real world, we have other sorts of constraints and things that will limit a population growing indefinitely without bound. But we're not going to overcomplicate this model right now. Sometimes if you take a calculus class in the future, you might look at more precise models for population growth that do take into account things like limited resources, etc. Okay, so here's an example. The number n of bacteria present in a culture at time t in hours obeys the law of uninhibited growth. Okay, so they're telling us it follows this model, and in fact, they were so super nice, they even gave us the equation. Determine the number of bacteria at t equals 0 hours. All right, you can plug it in, or you can just look at the fact that, hey, this is n naught. That's the population when t is 0. If you're not comfortable doing that, though, we can plug it in, sure. So n of 0 is 1,000 times e to the 0.01 times 0. So that's going to be 1,000 times e to the 0, which is 1,000 times 1. So we have 1,000 bacteria to begin with, right? All right. Oh no, I want to box this. Okay. Very good. What is the growth rate of the bacteria? So the growth rate is what k is equal to. K is the constant in front of t in the exponent. Can you see what k is equal to? It's 0.01. So as a percentage, that's 1%. We have a 1% growth rate. Very good. Now, what is the population after 4 hours? So how would I figure that out? Well, they're telling me t is equal to 4, so I'm going to go back to the model and substitute in 4 for t now. So n of 4 is equal to 1,000 times e to the 0.01 times 4. And this you can just punch into your calculator, okay? You don't need to show any work besides the setup. Let's round everything to 2 decimal places. The problem typically will specify, or it should be somewhere in the directions, okay? If not, then just use your judgment. And you should get approximately 1,040.81 bacteria. All right, does that seem reasonable? I mean, if the growth rate is 1%, yeah, after 4 hours, a little more than 40. All right, now they're asking when will the number of bacteria reach 1,700? So this time they want to know when n of t is equal to 1,700. So I'm actually going to set the equation equal to 1,700. So that equals 1,000 e, and I'm going to solve for t, right? The question said when, so we don't know what time is. So to start solving for t, I have to divide both sides by 1,000. Get rid of that constant in the front. And, well, 1,700 divided by 1,000, that's nice. That's just 1.7. equals e to the 0.01 t. Okay, from here I can just take the natural log of both sides. So I have natural log of 1.7 equals natural log of e to the 0.01 t. But then remember, natural log of e, that's just going to cancel out. So all I have is 0.01 t. I'll continue it here. ln of 1.7 equals 0.01 t. So t is equal to ln of 1.7 divided by 0.01. You can just punch that in your calculator. And you should get about 53.06 hours. Okay, make sure you include units, especially if the units are given in the problem. So they told us here t is in hours, so make sure you include that on your answers. All right, last part of this question says, when will the number of bacteria double? Okay, so if we started with 1,000 bacteria, doubling would be when we had how many? 2,000, right? So this is going to be very similar to the last problem. I'm just going to set it equal to 2,000 instead. And then I'm going to show you a shortcut, okay? So I have 2,000 equals 1,000 e to the 0.01 t. Same thing as last time. I'm going to divide both sides by 1,000. And then we have 2 equals e to the 0.01 t. Again, like last time, let's take natural log of both sides. So ln of 2 equals 0.01 t. So t equals ln of 2 divided by 0.01, which is about 69.31 hours. Okay, now let me ask you guys this. Was it important at all that we started with 1,000 bacteria when we found the doubling time? Like if we had started with 50 instead, then this would have been 100, right? Whatever the initial is, the doubling time is twice that. So what ends up happening is whenever you're trying to figure out the doubling time, you're at this step here where you have 2 equals e to the kt. And then you're going to end up with ln of 2 equals k times t. So t equals ln of 2 divided by k. So if you just want to cut to the chase, that's your doubling time right there. All right. Ooh, what if someone asked you for the tripling time? What would change? Can you figure it out? It would just be ln of 3 over k. Okay. That's the tripling time. If you hate that, it's fine. You can always just set the equation equal to whatever double the initial population is and solve from there. You don't have to do it this way. All right. Let's look at another example here. A culture of bacteria obeys the law of uninhibited growth, okay? They're basically telling us when they say that we can use the model that was given on the previous page. Not with the same constants, but the same general setup. So if n is the number of bacteria in the culture and t is the time in hours, express n as a function of t. So all I'm going to do is rewrite the law of uninhibited growth. N of t equals n naught times e to the kt. All right, that's it so far. Part A was nice, right? B, if 500 bacteria are present initially and there are 800 after 1 hour, how many will be present in the culture after 5 hours? Okay, let's go through piece by piece. So 500 bacteria are present initially. That's n naught, right? That's the initial amount. And then they tell me there are 800 after 1 hour. So what I'm going to do is use this piece of info to find k. And then once I find k, then I can answer the last part of the question. How many will be present in the culture after 5 hours? I'm going to worry about that last. Okay? So let's write out what we have so far. I have n of t equals 500 e to the kt. So right now I don't have k, but they did tell me there are 800 bacteria after 1 hour. So I'm going to go ahead and substitute that in now. So I'm going to replace n of t with 800 equals 500 e to the k times 1. All right, good. Now let's see, we got to solve for k. So I'm going to divide both sides by 500. Divide by 500. 800 divided by 500 comes out really nice. 8/5 or 1.6 equals e to the k, which means k is equal to natural log of 1.6. Okay. So now let's put that back into the original model. So that means n of t is equal to 500 e raised to the ln of 1.6 times t. But you guys, e raised to the ln of 1.6 is just 1.6, right? So if you'll recall, if you have e to the natural log of x, that equals x. So if you have e to the ln of 1.6 times x, that's 1.6 raised to the x. Oh, okay then. That means I can write this model now as n of t equals 500 times 1.6 raised to the t. So now the base is 1.6 instead of e. It's really up to you, and check with your instructor if they want you to take this step or not. Some are totally fine with you figuring out what this is as a decimal and rounding it and using it that way. It's just this is more precise. However, now the base isn't e anymore, and not everyone loves that. So just check with your instructor, okay? Cool. Now we can answer the question. It says, how many will be present after 5 hours? We got it. I'm going to plug in 5 for t. So n of 5 equals 500 times 1.6 to the 5th. And just punch it in your calculator. You should get about 5,242.88 bacteria. Okay. Good. Now, part C says how long until there are 20,000 bacteria. So in this case, I'm going to go to the model here. Let me box it so you can find it quickly. And I'm going to substitute 20,000 for n of t. So I want to know, when is the population going to equal 20,000? So this is 500 times 1.6 to the t. So to solve, we're going to divide both sides by 500. Cancel, cancel. And now we have 40 equals 1.6 to the t. Again, we're going to take the natural log of both sides. So I have ln of 40 equals ln of 1.6 to the t. And then do you remember solving logarithmic equations like this? We just did it in 2 lessons ago. You can move that exponent to the front now. So I have ln of 40 equals t times ln of 1.6. And so t equals ln of 40 divided by ln of 1.6. And this is approximately 7.85 hours. I had 849, but I want to round consistently. Okay, good. So that's it for the law of uninhibited growth. Now we're going to look at the law of uninhibited decay. Same exact model. It's n of t equals n naught times e to the kt. Only difference is K is negative, which means, remember your exponential functions? If you have e raised to a negative x, that means the graph is being reflected over the y-axis. So you have, instead of a growth model, a decay model like this. Oh, yeah. Also, did you notice something about this model? It should remind you of the continuously compounded interest formula, the PERT formula. And they're essentially the same. Instead of P, the principal, we have N naught, that's the starting population. And then instead of A for final amount, you have N of T. But it's the exact same thing. Our interest rate is now K, either growth rate or decay rate. It's all the same thing. Now, definition. All radioactive substances have a specific half-life, which is the time required for half of the radioactive substance to decay. So basically, it's the reverse situation from a population doubling. It's the starting amount disappears by 1/2. Half of it decays. Okay? So first example, we're starting off nice and breezy because they're giving us the equation. You should always do a little dance rejoicing when this happens. Iodine 131 is a radioactive material that decays according to the following function. Cool. Where A naught is the initial amount present and A is the amount present at time t in days. Days. Now assume that a scientist has a sample of 100 grams of iodine 131. So when they tell me that he has 100 grams to start off with, that's the A naught. Okay, so in this problem, they're using A's instead of N's. No big deal, guys, no big deal. All right, what is the decay rate of iodine 131? So the decay rate is basically K, right? Go to the exponent, and it's the constant in front of T. So K equals negative 0.087. As a percentage, that's 8.7, right? Now, since this already states the word decay, it implies that it's negative. So I'm not going to add an extra negative. I'm just going to say the decay rate is 8.7%. If they said, what's the growth rate? Then I would say negative 8.7% so that they know it's actually decaying. But since they already said the word decay in the problem, they know it's negative. All right. Good. Part B. How much iodine 131 is left after 9 days? So let's go plug in 9 for T. A of 9 is going to equal, remember, A naught is 100. So we've got 100 times E to the negative 0.087 times 9. Just punch all this in your calculator, and you should get approximately 45.70 grams. Right? They told us it was in grams, so we're putting the units on there, guys. Grams. Okay, easy enough. Part C. When will 70 grams of iodine 131 be left? So am I plugging in 70? No, I'm setting the function equal to 70. So 70 equals 100 e to the negative 0.087 times t. And now let's find t. How do we start? They all start the same. Divide by 100. You want to get that exponential term all isolated. So 70 divided by 100, that's 0.7 equals e to the negative 0.087t. Take the natural log of both sides, so ln of 0.7 equals, and then all I'm left with is negative 0.087t. Divide by the coefficient on t, so t equals ln 0.7 over negative 0.087. All right, so I get approximately 4.0997. So we could just round that to 4.10 days. Very good. How are we doing? If you just remember it's the PERT formula, you really can't go wrong. Last part, what is the half-life of iodine 131? So when they're asking for the half-life, you're finding T. You're finding the T that it takes for half of the initial amount to decay or to remain. Depends if you're a half full, half empty kind of person, huh? So if we start with 100, that means the final amount is going to be 50. So that would equal 100 e to the negative 0.087 t. Then the rest of the problem falls into the same way. So 1/2 dividing by 100 equals e to the negative 0.087 t. Then we have ln of 1/2 equals negative 0.087 t, which means t equals ln of 1/2 over negative 0.087. And punch it in the calculator, you should get about 7.97 days. Notice half-life is very similar to when we were finding doubling time in the previous problem. Did you figure out what the shortcut formula is? T equals ln of 1/2 over k. So feel free to use that, because remember, the initial amount is irrelevant. You just want half of it to be left. So you're always going to be at this step right here, where you have 1/2 equals e to the kt when being asked to find the half-life. Sometimes they like to be extra sneaky and they don't even give you the initial amount because you don't need it to find the half-life. Okay, one last example. It's a fun one. So the half-life of radioactive potassium is 1.3 billion years. Can you believe it? Okay, if 10 grams is present now, how much will be present in 100 years? And then how much will be present in 1,000 years? Okay, so we're going to use our decay model. N of t equals n naught e to the kt. They gave me n naught. They said 10 grams is present now. So I'm going to rewrite this as n of t equals 10 e to the kt. Okay, well, they didn't tell me what k is yet. They did tell me the half-life. The half-life is 1.3 billion years. Let's put that in scientific notation. Who wants to be writing zeros all day long? Not me. So that's 1.3 times 10 to the 9th. I need to find k. Well, they gave me the half-life. You see the formula I have boxed up above? Can't I find k if I know what the half-life is? I sure can. So let's go ahead and find k. They gave me the half-life. This means that k times t is equal to ln of 1/2, right? Where this is half-life. That t is a special t. That's the half-life t. So that means k times t is ln of 1/2. So k equals ln of 1/2 over t half-life, which I know is 1.3 times 10 to the 9th. So this is ln of 1/2 over 1.3 times 10 to the 9th. Guys, it's going to be super small. So I have about negative 5.3319 times 10 to the negative 10th. If your calculator can store values, store it. That's k. Okay, so let's put it back in the model. So we have n of t equals 10 times e to the negative 5.3319 times 10 to the negative 10th times t. Okay, this is what we're working with. Now, let's see what the problem's asking us for. How much will be present in 100 years and then in 1,000 years? So I'm going to plug in 100 and then 1,000 for t. So n of 100 is equal to 10 times e to the negative 5.3319 times 10 to the negative 10th times 100. Well, 100 is 10 squared, right? So this is 10e to the negative 5.3319 times 10 to the, I have negative 10 plus 2, negative 8. And then if you punch this in your calculator, you get about 9.999999467 grams. Yep, 1, 2, 3, 4, 5, 6. I just wrote out everything that was on the screen in my display. Now stop and ask yourself, does this make any sense? So we started with 10 grams. The half-life is 1.3 billion years. So it will take 1.3 billion years for us to go from 10 grams to 5 grams. So if we've only gone 100 years into time, that's nothing compared to 1.3 billion years. So yeah, we should have pretty close to the original amount. I don't expect much to decay. And I don't think a whole lot's going to change if we do n of 1,000 either, right? So yeah, this answer is making sense. It's strange, but it makes sense. So n of 1,000, that's going to be 10 times e to the negative 5.3319 times 10 to the negative 10th times 1,000. So that's 10 cubed. So this is 10e to the negative 5.3319 times 10 to the negative 7th this time. And you should get 9.99999. Whoa, they're all spread out. Hold on, let's write this nicer. 5 nines. I've got 5 nines. 1, 2, 3, 4, 5. And then a 4, 6, 6, 8. So, you know, a wee bit more decayed, but not a whole lot. Okay, we're not even close to 1.3 billion years, which is when we would have only 5 grams left. All right, so that concludes the lesson. I hope you enjoyed it. And you can see how this model has its limitations, but also is very useful. Don't forget to give the video a thumbs up, subscribe if you haven't already, share it with your classmates, whoever you think would find it helpful, and stay tuned. Guess what, guys? We got trig coming up next. Oh yeah.